So this is example number 2. This example is for a parabolic airfoil. For a parabolic airfoil, the equations, this particular airfoil that's parabolic has this, these are the equations for the for the top and for the thickness and the camber equations are equal to this. Okay, so the first thing we want to do is, so let's get started here. There are a couple information, a couple of things I'm going to need as we do all these answers. The first thing is I'm going to need this information, so I'm going to take the derivative of this. 0.4 minus 0.8 x over c, that's given in the problem. We're going to need to do this substitution because we did that in class. So might as well do it now. So you get partial of eta respect to x. That would give you 0.4 minus 0.8, 1/2, 1 minus cosine of theta. So if you do your math, this gives you 0.4 cosine of theta. Okay, so given that, so I could go ahead and now replace all this inside the following equation. A sub 0 is equal to 1 over pi, because I need to know the value of A sub 0, partial of eta c x theta d theta minus alpha. And this whole expression is 1 over pi, 0 to pi, 0.4 cosine of theta, you can see it right here, d theta minus alpha, and this is actually equal to 0, so this whole expression is equal to minus alpha. Okay, so the next coefficient I want to find is, what is an, because we need an. 2 pi, 0 to pi, partial of c respect to x theta, cosine of n theta d theta. So that's the expression. So what we know that this expression is 0.4 cosine of theta. Because it's cosine of theta, you can see that this is going to be, this expression will be, this expression is actually the integral, the whole integral will be equal to 1. It's going to equal to, sorry, pi over 2 if n, if n is equal to the same coefficients, they are the same. This is 1, this is 1, so it has to be 1. For any other value of n, then that's actually any value different from 1 that would be equal to 0. Okay, so immediately we know that n is going to equal to 2 pi. Okay, if I want to write it complete, not to jump any steps here, cosine of theta, d theta, sorry, cosine of theta, d theta. This gives you pi over 2 multiplied by 0.4, but this is a constant, so this gives you 0.4. A2, the expression A2, let's write it on the next page, is equal to 2 pi 0.4 cosine of theta. This is cosine of 2 theta d theta. So immediately you see that these are different. Because they are different, this is equal to 0. See, it's not, to find this coefficient is not that bad at all. You just have to be systematic in how you do this. Then now let's go ahead and apply our equations, because you're working with thin wall airfoil structure, thin wall airfoils. This is replace replace a sub 0 minus pi, and I'm sorry, just you may want to fix this. This is actually 1. Okay, this is equal to 0.4. So if I replace everything inside here, this gives me 2 pi alpha plus 0.4 times pi. And the pitching moment coefficient is 1/2 minus 2ac, replacing all the values in there, plus 0.4 x over c minus 1/2. If I want to find what your coefficient of pressure is, the coefficient of pressure will be pi 2cl minus a sub 0 plus a1 minus a2 over 2. Replace all the values in there. That gives you pi 2 pi alpha plus 0.4 pi minus alpha plus 4 minus 0 over 2. The whole thing gives you alpha plus 0.4 divided by 4 times alpha plus 0.8. Okay? So that's the expression that you end up with. Okay? And then if you wanted to do it, you could do it. I will leave that for you to show this for yourself. This is equal to 0, and you can show that your aerodynamic center again is over 4. Has to be that because it is we are working for a thin wall airfoil structure, and add x at the aerodynamic center c over 4. Your pitching moment is equal to minus alpha pi 1 over 2 minus 2x over c plus 0.4 pi x over c minus this. So if I evaluate this now at the pitching moment, so you find this is minus alpha pi 1/2 minus 2 c over 4 1 over c plus 0.4 pi. This is c over 4 1 over c minus 1/2. You can do a little bit of mathematics here. I will let you do that, and you can show that this value is minus 0.1 pi. Okay? So we have the pitching moment, we have your lift. Now we want to find a coefficient of pressure, theta. This looks a little bit more messier, but it's not that messier. This is plus minus gamma theta, v infinite plus 2, n equal to 1 infinite, b infinite cosine of n theta, where bn is equal to 2 pi 0 to pi partial of nt respect to this theta, sine of n theta d of theta, and remember this is nt is equal to this, so I can use that expression to I can plug that expression inside here, and then the expression I get, I can plug it back inside there. And we derived this kind of in the class. But I will let you do this, the whole mathematics of this. This is 1 plus cosine of theta, sine of theta minus 2 v infinite n equal to 1 infinite an sine of n theta, and note that a sub 0 is equal to 1 over pi, 0 to pi, partial of eta, partial of x, theta, d theta minus alpha. This is minus alpha. An, we just found it, and I told you that an is equal to 0.4, and a2 and on will be 0. Okay, so I can take this expression, the whole expression, I'll simplify. That means you only have two terms here. You have 0, the term that has 0, and a term that has 1. So this actually becomes a sub 0, sine of 0 is 0, so that term actually goes to times 0, plus a 1 times sine of theta 1, and this is 0.4. Okay, so, and this is also equal to minus alpha. So if I did the whole thing and you replaced everything inside here, divided, you find that this is equal to 2 v infinite minus alpha 1 plus cosine of theta sine of theta minus v infinite 0.4 times 2 sine of theta, and then for convenience we can divide everything by v infinite on both sides. Why am I doing this? Because that's the expression I need over here, you can see. So I found that expression. Let's move to the second expression. The second expression is bn. So bn is equal to 2 over pi, 0 to pi, partial of eta, partial of x of theta, sine of n theta d theta. We know that this is equal to if I divide by c, 0.1 x over c, 1 minus xc. The derivative of this respect to x then will give you 0.1 minus 0.2 x over c. Do the same replacement as we did before. C, 1 minus cosine of theta, and this will give you 0.1 cosine of theta. So this is the expression that will go inside there. Okay, so what is true for this problem is the following. Bn is equal to 2 over pi, 0 to pi, 0.1 cosine of theta, sine of n theta d theta, and this has two expressions. When n is equal to 1, b1 is equal to 0. Remember, n and n go out court. When n is equal to even, then what you can show is that bn is equal to 0.4n. You can do that mathematic for yourself. When n is equal to odd, it's an odd number, then bn is equal to 0. Okay, so to make our lives easier and to ensure that we are always working with even numbers, this is a mathematical trick that we always do. This ensures that we are always even. Okay, that was the case. Then bm is equal to 0.8 m pi 4m squared minus 1. Remember, I replaced here 2m because then m ensures that this number is always going to be even. You don't have to worry about this. Okay? So we are almost there to find the coefficient, the pressure coefficient at the upper surface will be minus 2 times alpha 1 plus cosine theta sine of theta minus 0.8 sine of theta plus, and remember now we changed this to m, and there's no problem because we already ensured that this is actually going to be even every single time. M squared minus 1. Cosine, remember instead of n, I need to put 2m. Okay. Then same thing. I'm going to just copy. Okay. And so just change a few things here. This is negative. This is going to become plus. This is going to become plus. There is a 2 missing here. I'm sorry. There's a 2. Don't forget that 2. So that will be your expression. This is your coefficient of pressure, top and bottom surfaces. And what you can do is, the more terms you put, the more accurate you come. You get closer to what the expression looks like. Okay. This wraps up example number 2 on parabolic airfoils.